Hello, my name is Chris Romaine. I'm pursuing a Bachelor of Science in Electrical Engineering, and I'm team leader for the Green Energy Automation and Optimization System. My responsibilities include team coordination, high and low voltage systems, as well as printed circuit boards.
Hi, my name is Ferraresi. I'm a computer engineer and computer scientist. I'm the embedded systems team leader, and I have developed the user interface and control subsystems of the GEAOS.
Hi, my name is Rabbany. I'm doing my Bachelor of Science in Electrical Engineering with the Computer Science minor. I'm in charge of electrical subsystems, hardware design, implementation, and installation.
My name is Barbara Allende and I'm a computer engineering major. I am in charge of the database collection system and the user interface.
We would like to introduce you to the fifth member of our team, lovingly referred to as GEOS. This is our functioning proof of concept prototype. Our team came together due to a common interest in renewable energy and a passion to engineer innovative solutions for a green energy future. Furthermore, having two students of each discipline, electrical and computer engineering, struck the perfect balance required for the design and implementation of this project. Global energy consumption has increased exponentially in the last century. The 2018 release of the Intergovernmental Panel on Climate Change report sheds new light on the dangers of continuing our current carbon emissions path. Experts warn the planet has until 2030 to stem this catastrophic climate change. The burning of fossil fuels contributes to the many problems related to this global epidemic of greenhouse gas emissions. Research and development, combined with government subsidies, have brought the cost of renewable energy to parity with fossil fuels in most markets. However, renewable energy systems require a substantial upfront investment on the part of the consumer. The GEOS team looked for ways to enhance the financial advantage of green energy systems in order to motivate their implementation. Our research identified three deficiencies with the current state of the art. Existing systems fail to optimize the use of generated energy, maximize battery life, or incorporate Internet of Things technology. The GEOS hybrid load management system addresses these issues by reducing the levelized cost of energy to increase the stakeholders' return on investment. Furthermore, the incorporation of Internet of Things technology provides attractive user functionality.
Here we can see the heart of the GEOS system, which efficiently manages power both automatically and manually. This is possible through a serial communication provided by a USB cable connected from the single-board computer to a slave microcontroller. Automatic control is standardized based on power levels. This means that loads are shunted according to their priority on the overall energy of the system. Multiple devices are used to make the GEOS work properly. Voltage and current sensors in blue can be found on the periphery of the case to the left of the microprocessor. These sensors measure current and voltage of the loads, panels, and battery, which remaining power is also shown by a neopixel ring to the right, going from red, yellow, and green accordingly. Relays on the bottom of the microcontroller are responsible for alternating between grid and green energy power panels, as well as switching the loads on and off. Because of the IoT capabilities of the GEOS, override of automatic control to enter manual mode can also be achieved in several ways. Remotely from any location with internet connection, with a mobile phone, or simply through the central interface. An LCD screen is attached directly to the single-board computer, which serves as the graphical platform. This method provides an user-friendly environment composed of several views that allow for system automation and load management in real time. The code for the GEOS is developed in two parts. The microcontroller code is written in C for Arduino. This code is responsible for measurements and control of all devices, as well as data processing and delivery. The control subsystem functions automatically, however it can be overridden by the central computer. The Raspberry Pi computer utilizes several Python-compatible libraries and other development tools to power the graphical user interface that uses Debian distros and Raspbian operating system as its platform. The main challenge between the two controlling devices is that communication must be scheduled. Data pipelining, string sanitation, and proofing, paired with timers, make dual communication responsive. Data itself is easily stored using local database management systems, but can also be accessed wirelessly on the cloud. This view of the interface displays the status of the loads and allows for changing of the source of power. Battery life is integrated in the system design and affects how energy is managed. In the scenario of an outage, battery power will be all the system is running on. Therefore, GEOS will prioritize critical loads, shunting the remaining loads off. It is important to notice that auto control is off at this point, but any changes to the automatic program will override this mode. The Power View monitors and records battery and load data with a unique timestamp. The information is displayed on the view in real time using a threading system that allows for control with no interruptions. On the right, total power from both panels is also measured for data collection and statistical analysis purposes, which are used to create preferences, modes, and suggestions that cater to the user needs.
Construction of the GEOS began with the selection of sensors and output components with the proper specifications. Safety and functionality were the main concerns in this process. The next step included the testing and calibration of all sensors using an oscilloscope in our lab. This enabled us to manually adjust for an acceptable level of accuracy and precision. Code was then written to translate samples of the sensor readings to be used by the system. Once implemented, the system was tested under working conditions to verify the results.
GEOS team's future plan includes future code development that will expand the Internet of Things technology to promote awareness and conservation of power consumptions. The GEOS team also plans to take entrepreneurial initiative to do market research and produce a business and marketing plans. Our final step is to build a commercial prototype and have it tested and certified by Underwriters Laboratories. In conclusion, we'd like to thank the following people: Ms. Regina Gonzalez, Mr. Perry Wenthal, project advisors Dr. Roger Messenger and Dr. Amir Abtahi, Dr. Hanky Zhuang, and a special thanks to Mr. Michael Schimpanzi for his fabrication expertise and assistance, and finally, FAU Web Program.